Hello, good morning. My name is Ashutosh Garg. I work for Furnace Improvement Services. Welcome to our webinar on refractory and heat loss calculations. 2 years ago, we decided to do a 12-part series on fire heater design, and this is the ninth webinar in that series. We will be covering refractory and heat loss calculations. Refractory lining in a fired heater is a very important component. Most of the people don't realize the importance of refractory because they are not able to see the function of refractory. But when you look at the radiant section, it has refractory. You look at the convection section, it has refractory corbels. You look at the breaching, you look at the stack, it has refractory. You look at the hot flue gas ducts, cold flue gas ducts. Almost every piece which is dealing with high temperature has refractory lining, including burners. So refractory is a very important component and we will be covering it today. Uh, Before we start, I need to talk a little bit about our company because they are the ones who are paying the bill for this webinar. So Furnace Improvement Services started in March of 1996. Next year we will be completing 30 years. We have our engineering office in Noida, India. And Furnace Improvements is a different type of heater company with a contrarian approach. And as a result of that, we have 3 patents on fired heater design or fired heater improvements. We have a patent on split flow for increasing the capacity of fired heaters, increasing the efficiency of fired heaters. The second one is on inclined firing technology, which is for reducing tube metal temperatures in fired heaters. And the third one is smart stack damper, which is for improving the draft profile or saving energy in fired heaters. We are full service heater vendor, but our model is little different because we work directly with the end users. And it's almost like a doctor-patient relationship. And we take pride in giving unique value-added solutions. Our mission is to improve the performance and efficiency of existing fired heaters. We also build new fired heaters. So we can do anything and everything what a regular heater company can do and more. So our philosophy has been very straightforward. Do it once, do it right. Because of time difference between India and US, we are practically working around the clock. We keep schedules. We have done heater supplies in about 6 months' time. And we request you to challenge us with your project. If we have the worst heater in your refinery, give it to us and we will convert it into the best heater in your refinery. That's our challenge. We work on all types of fired heaters in the refinery, starting with crude heater, vacuum heater, reformers, cokers, hot oil heater. We also do CO boilers. We do waste heat boilers. We do SCR units. We do ultra low NOx burners. So we can also do steam methane reformers. Right now, we are working on a large project for an SMR, upgrading the convection section, improving the efficiency by 7%. So we can do almost any type of fired heater. This is a list of our clients. The most important client is number one, Phillips 66. We have a master service agreement with them for almost 20 years now. We do a lot of work. In addition, Citco has been our repeat client for a long time. They gave us the first new fire heater. They gave us the first split flow installation. They gave us the first or the second inclined firing installation. So we have had good relations with Citco, Countrymark, Delec. Most of the work what we get from our clients is through word of mouth. We are not big enough for advertising in hydrocarbon processing or printing flashy brochures, doing flashy presentations. So most of the word what we get is through these webinars, through these uh, articles, and word of mouth through our performance. As far as capabilities are concerned, we are a process focused company. We have 7 process engineers and 7 mechanical engineers. So we kind of focus more on process and CFD to analyze the root cause problems in fired heaters. That's what our motto is, to analyze and eliminate the root cause so that you won't have problems later on. We also can do structural design, we do mechanical design, we have 3D modeling, we do on SolidWorks. We are the only heater company which does its own fabrication drawings using 3D, and because of that, we are able to execute projects very, very fast. When it comes to CFD, we specialize in combustion, airflow distribution, fan suction, discharge ducts, AIG for SCR units, and flow distribution in manifolds. So we can do CFD analysis and find out what's wrong. If you have any issues in combustion, airflow distribution, we can help you there. This is just a graphic description of the 3 patented technologies we have. We have about 12 references for split flow and approximately 12 references of inclined firing. Any new heater we supply, especially the vertical cylindrical heater, has inclined firing built in. So you get this technology free of cost from us when you buy a heater from us. And then we have about 4 installations of smart stack damper. So let's talk about and come down to now to our webinar. And what are we going to talk about? Why refractories are essential. What are the key parameters on refractory types and their applications, refractory anchors, common causes, and then in the end we will talk about the heat loss calculations. So just to tell you a little bit big background of myself, I worked for about 16 years in India before I came to US. And in India, I saw a number of refractory issues, number of refractory problems in fired heaters, and especially with the castable material. And later on, I realized that castable installation is very, very critical. If you don't follow the correct procedure, the castable won't last long. In fact, there was a heater, a brand new heater, where I would touch the castable and it would start falling. Then when I came to US, I saw even more problems. I saw companies using ceramic fiber in convection section and that getting lodged in the fin tubes, blocking the convection section. So lots and lots of problems I have seen on ceramic fiber, castable. So you have to be very careful to make sure that you don't get into those problems. Anchors is a big issue. So we will talk about it. So let's start. If you look at this sketch from API 560, This is giving you a cross section of the fire heater, and if you see, it has side walls, refractory side walls, which has refractory lining. I mean the side walls. Then we have the arch, which has a refractory lining. Then we have convection side walls. It has refractory lining. Breaching, stack, end tube sheets, header boxes. So refractory lining is almost practically everywhere. And this one even has a gravity wall, for maybe for poker or for some special units. It's showing that, so even that is a special thing. There have been cases where this refractory wall fell down or started inclining, those type of problems have also happened. So what is refractory? Refractory is an insulating material for controlling shell temperature and ensuring that operators don't see high temperature. So refractories are non-metallic, porous, and heterogeneous materials, which are thermally stable in the sense they can go up to 3000 degrees F. And the purpose is you create a thermal resistance so that you can contain high temperature, which is happening in the radiant section, convection section, burners, it can withstand high temperature. So that's basically the definition of refractory. Uh, Before we move on, my team has come up with this refractory terminologies, and we have taken it from APFI 60. These are some of the things which you need to understand when you're dealing with refractory. Ambient temperature plays an important role, especially if you're in a cold climate. Your heat loss will be much, much higher. Hot phase is the refractory exposed to the furnace or flames. Hot phase temperature is the temperature of the refractory. Thermal resistance, cold phase temperature. So these, I mean, I'm not going to go over all of these, but what I suggest is go through the API 560 document. Try to understand these different terminologies. Interface temperature is the temperature between the two layers of castable or two different refractory layers. Then refractory design temperature. So API says it should be at least 300 degrees higher than the operating temperature or your design temperature. That's how the refractory should be designed. Wind velocity also plays an important role in heat losses. Thermal conductivity, of course, is the most important parameter. Emissivity is also important for heat transfer. So all these parameters, insulating refractory, dense refractory, flue gas velocity, again an important. There have been cases where I said people use ceramic fiber in convection and then it caused a lot of problems. Vapor barrier, we try to provide some sort of a vapor barrier between two layers of castable so that the moisture doesn't percolate into the dry layer. Spalling is the breaking of refractory on the hot phase due to thermal stresses or uh, water coming out, so the refractory can spall. Maximum service temperature, alkaline hydrolysis, anchor tie packs. So these are some of the ceramic fiber. We will talk a lot more in the presentation today. So what is the need for refractory? Reduce heat losses through casing and improve energy efficiency. Prevent steel casing and substructure from overheating. It's basically absorbing the heat and then radiating it back to the tubes. So that's basically the three functions of refractory. You need refractory even in thermal oxidizers, incinerators, reactors. You need steel mills are the biggest consumers of refractories. So if you look at fired heaters, we are talking about three major sections: radiant, convection, stack. And I already talked to you that everything has refractory. This is the air preheater, so even the hot air duct has refractory, the plenum has refractory, floor has refractory. Everything has refractory, all the way up to the top. So what are the things which are important? And I want to tell you that things have improved a lot, in the sense that for the last, I would say about 30, 40 years in US at least, we have stopped firing fuel oil. But in other places in the world, that fuel oil firing continued for a long, long time. And fuel oil firing is very, very tough. Fuel oil has sulfur, fuel oil has sodium, fuel oil has vanadium. So they not only attack uh, high temperature components like intermediate tube sheets and tube supports, but they also attack refractory. So that is one good news when we talk about refractory system these days, because the fuel is much, much better. We're talking of fuel gas firing. Even in fuel gas firing, they have limited the H2S content to 160 ppm. So things have become much, much easier. You are not worried about ash corrosion. You are not worried about you know sulfur, vanadium, sodium, etc. Now, when you come to convection section, if you have soot blowers because of any reason, because of this thing, then that requires a special refractory in that area. Then we have burner blocks because they are high temperature, so you need very, very high alumina refractory over there. So generally, when we are selecting or designing refractory, we have a standard developed by API to be used for heat loss calculations. So no matter what is your ambient air, you generally use about 80 degrees F or 27 degrees centigrade as ambient air. Wind velocity is 0 miles per hour, still air. Emissivity of the surface is used as 0.8. Hot phase temperature is typically whatever temperature you have plus you add 300 degrees. Cold phase temperature, what we want to control, should not go above 180 degrees. That's generally this thing. Except for floor and stack. Floor we permit it to go up to 195, and stack normally we don't care actually because nobody is going to touch the stack. But one thing which has to be very important is you want to make sure that your heat losses are no more than 1.5 to 2.5 of the total heat release. And this can be misnomer if you are living in Europe, because of the low ambient temperatures, your heat loss could be much higher, even though your casing temperature is 180, your heat loss could be much, much higher. So how do we select the right refractory? What are the parameters actually? We are looking at the hot phase temperature, interface, cold phase, design temperature, maximum continuous use temperature, thermal resistance or thermal conductivity, fuels fired, abrasion resistance, gas velocity. So these are some of the things you want to look when you're selecting the refractory. So what are the different types of refractories are available to us? We have Firebrick lining, in which we have typically dense firebrick or insulating firebrick. Then monolithic linings are castables or concretes. And there also we have a choice of shop mix or field mix. Ceramic fiber lining, we have a choice of blanket, board, or modules. Insulating block. So these are some of the materials which are available, And sometimes it leads to confusion because you have a choice of so many materials. Which one should I be using, So that can also be challenging. So typically lining, most of the time we go for single lining, and that is the easiest and cheapest. In several places we may go for multi-layer, and multi-layer means we are using two refractory materials, different refractory materials. It could be castable and block. It could be two mixtures of castable. It could be brick and block. So there are different combinations we can use. So that is what is important here. So let's talk about the target walls. These are used in the heaters. No, they are not very common anymore, except maybe in some coker heaters, or maybe in some platformer heaters or UOP reformer heaters for dividing the cells. They are made out of high density Firebrick, and they have a lot of weight actually, because we want to make sure that the base is stable. So the maximum height is about 25 feet, 24 feet, and the base has to be 8% minimum of the height. So it becomes pretty 1 by 12. So about 2.5 feet of, base will be required for 24 feet tall brick wall. Yeah. So they are there, they are long lasting. Most of the time, if they are constructed properly, they would be long lasting, but sometimes they do uh, crumble. So let's talk about the brick layer. Brick, insulating fire brick is still used in very high temperature cracking furnaces, because there other materials are not suitable. So we use insulating fire bricks. Insulating fire bricks also have the resistance to withstand flame actually. So that's another property we use it for. And we use mortar to tie these bricks together, and then we provide vertical expansion joints. You know, second material, which is a recent material. I mean, not so recent. It's, I think, came out in 1950s or 60s. Ceramic fiber is almost like cotton, and it's made out of aluminosilicates. The good thing is it has a very low thermal conductivity as compared to castable and bricks, and that also has a low density. And because of the form, it also absorbs a lot of noise. So heaters which are lined with ceramic fiber are a lot quieter as compared to heaters which are lined with castables. So these are some of the advantages of ceramic fiber. As I said, low heat storage, lower thermal conductivity, very light. Transportation cost is low, no damage during transit. You don't need to cure it or dry it out. So these are some of the advantages. The disadvantages, especially shrinkage at high temperature. That's why we don't prefer it in cracking furnaces. Not resistance to high flue gas velocities, and sometimes they could be more expensive than conventional refractories. So we this ceramic fiber normally is made in 1 inch thick fibers. 1 inch thick blankets is normally how they are made, and we have the anchors over here. You can see this thing, and you kind of impale the walls. impale this blanket on these anchors to develop 1 inch layer. Then if you want 6 inch layer, then you put 6 layers. Sometimes we are even using a backup layer nowadays to make sure that the heater surface is uh, smooth or does not have too many this thing. So one of the downsides you can see is it's not good for heaters which have sodium or sodium plus vanadium, which starts getting fluxes. It's also not good in convection section stacks or ducting. But other than that, it's very nice. As I said, 1 inch layer is the standard thickness of this. And density is 8 pounds. It's available in 3 or 4 densities. 8 pound is very common. It's available for 6 pound. It's available for 4 pounds. The maximum flue gas velocity it can take is about 40 feet per second. And if you're using backup ceramic fiber, then it should be at least 6 pounds per cubic foot density. This is a picture of a ceramic fiber duct they have made. Other improvement material is ceramic fiber board. Ceramic fiber board has a much higher density. Instead of 8, it has double, almost like 15 pounds per cubic feet. It can take velocities almost up to 12 meters per second. We can use it as a hot face layer if required, but it is very expensive. That is another downside of using ceramic fiber board is it's a very expensive material and you use it only when you cannot use anything else. Ceramic fiber modules is a very popular material. These modules are made prefabricated using blankets, and these blankets can be folded or edge stacked. This one is like edge stacked, you can see, and then there are other ones which are folded, one, two, three, four, and then they are pre-compressed and anchored, and they have become very common means of installation of ceramic fiber because the installation time is very fast. Generally, ceramic fiber modules are used wherever you need more than 4 inches of lining. Anything more than 4 inches, we can use ceramic fiber modules. Castable refractory. Castable is also a very good material. Uh, Historically, we always used to have bricks in almost all the heaters before 1950s, 1960s. And then we started getting castable. And castable is a mixture of three materials: luminite, hadeite, vermiculite. And we mix it in different proportions with water. And you normally have hydraulic bonding taking place at about 200 degrees F, 220 degree F, and then chemical bonding taking place at about 1000 degree F. So that's what imparts the strength. Now, you can mix these castables in different components, different ratios, and you can achieve the low thermal conductivity or what you are trying to achieve. So that can be done. And that is one reason the insulating castables are available in many grades. You know, we have castables ranging lowest is 1600, then 1800, then 1900, then 2300, 2500, 27. So every 200 degrees, all the way to up to 3000 degrees, you can get insulating castables available. The advantage is very easy to install, low cost, extensive variety, resistance to flue gas velocity, and you can install it in any thickness or any shape. One of the critical things or installation is very critical. You need to make sure that the water you are using is the right quality and at the right temperature and right amount. Other thing with the castables is you need a slow dry out. Approximately about 3 days. Typically it takes about 3 days to dry out the castable. It's prone to cracks, it happens, and also lot of wastage during installation. In US, most of the castable is applied using gunning, and there is almost like 50% wastage which takes place, which is due to rebounds. It is faster, but it does gets wasted. So these castables generally limited to 1900 degree F, and there are three common combinations of this LHV castable which are used in the industry or which were used in the industry. 124 as a hot face layer, 14 LH for the stack, and LV16 for backup, or even on the floor we would use these last. So LHV castables are called field mix castable. So that means you're buying the three components and you were mixing it in the field depending on your requirement. And people realized that the quality control was not good and lot of problems developed. So a lot of companies have shifted to shop mix castables. That means the castables which are supplied by refractory vendors, which are ready made, and all you need is add water and then apply it. So those are the shop mix castables. So LHV, coming about LHV illuminite is the cement. This is haydite, and vermiculite is the aggregate. So they basically take these three components and then fire it. Uh, these are just for giving you on the different sections in fire heaters. Sidewall arch burners, minimum 3-inch thickness is suggested. Header boxes, tap, breaching ducts, minimum 2 inches. Tube sheets, in tube sheets, we use 5 inches on radiant section. In convection section, we use 3 inches. And generally, you don't use more than 8 inches of castable. That's because it becomes very difficult to hold it with the anchors. So that's the reason we use no more than 8 inches of castable. So the need for drying out the refractory, because it contains a lot of water, and you need to dry it gradually so that you don't damage the refractory and you don't you know remove the water. So typically about 50 degree per hour is the maximum rate specified for castable lining dry out. And then whenever you reach 250 degree, we need to hold it for about 12 hours. Then at 500 degrees or 600 degrees, they're holding. And then go up to. So this is done very, very commonly. But the reason it is done is because if you don't do it, you will have alkali hydrolysis occurring in castables, and that will damage the refractory. Another thing which has happened is because nowadays people go for shop dry out. They don't want to take any chance uh, of the convection section or heater lying in the field and developing alkali hydrolysis. They ask heater vendors to do the partial dry out up to 500 degrees. Some people even insist on 1000 degrees in the shop. So we do that in the shop very often, and there are a lot of companies who specialize in this type of work only. So shop dry out has become almost like an industry standard for making sure that we don't develop alkali hydrolysis, because there are cases where the heater is sitting in the field for 2 years because the project got delayed. So you don't want to make ruin the castable lining. CFB versus castable. Always a tussle, should we use CFB, should we use castable, you know. Now CFB is more efficient, weighs lower, a better thermal shock, no need for drying, very easy to repair in the field. So CFB is very, very uh, advantageous material, but CFB we don't use it in the convection section or in the stack. That's generally our recommendation. Use castable in the stack and convection section. Insulating block. This is another material which I like, and this can be used as a backup. There are different varieties. It can go up to 200, 2000 degree F, and it helps in reducing the overall refractory thickness and also helps you in reducing the overall heat losses. So the casing temperature can be dropped substantially by using insulating block. Now, the some people don't like it is because when you use insulating block or when you use dual lining, your labor is going to go up substantially because you got to install the first layer and then you got to install the second layer, and most of the time there has to be some sort of a vapor barrier between the two which has to be provided. So a lot of vendors don't want to provide two-layer refractory lining, even though for the client it may be a lot beneficial, but it becomes more expensive, so they just stick with the single layer castable. Insulating Firebrick, I mean, I would use it anytime. The only downside is the labor. The installation of insulating Firebrick is very expensive. I mean, even till today, these bricks are laid by hand. I don't know whether they have come out with some sort of a robot now to install the bricks, but to the best of my knowledge, they have to be installed by hand. But other than that, it's a very good material, high degree of porosity. We can control the quality of the castable, quality of the brick a lot more efficiently. And you can get insulating Firebrick in the densities ranging from 35 to 70, you know. And this can be used in all areas of fire heaters. But as I said, the only downside we have not. In India, we used to see IFB a lot more often in the heaters, but in US, IFB is not used basically because of the high installation cost. Several good things going for it. It has good insulation, good hot load strength, already dried out, available in large variety of shapes and sizes, readily cut, you know, self-supporting type, lightweight. So very, very good material. So this is showing you how these how these bricks are installed. We have to put these brick holding clips and brick support uh, brackets, which are used, I think, every 14 layers. Every 14 layers, we use this. This one is showing a 3-inch block at the back and then 4-inch, 4.5-inch insulating brick in the front. So very, very common material, especially in ethylene crackers. It is still the material of choice. We use 3-inch and 9-inch. I think 9 inches should be 9-inch, so 12-inch of layer uh, brick and block lining is used in ethylene furnaces. These are some of the advantages: highly resistant to heat flow, very lightweight, stores much less heat, self-supporting, but labor-intensive kind of kill set. This one is showing the fire brick lining on the floor. Uh, Even this has been replaced by API, and they allow us to use 2500 degree F castable instead of the brick. So we don't use it anymore. But these bricks were used only for maintenance purposes or for people to walk on the floor. They had no other function. This is just showing you how the refractory bricks are installed, and as you can see, they are still installed by hand. This is a 9-inch thick brick which is being laid. Another important component in lining, especially in castables, is anchoring. Anchoring is supposed to hold the refractor in position, provide support for walls, arch, flat roofs, prevent bulging and bowing of lining, and allowing horizontal and vertical movement of lining. So anchoring depends on the type of lining and lining thickness, type of refractory material, anchor materials selection, and where are you applying the lining? Are you applying it at vertical, horizontal, roof, inclined, etc.? So that kind of depends or dictates how you will be putting the anchors. Uh, the good news is we have an API 560. To all those people who are listening, I call API 560 the Bible for fire heaters. So if you want to be an expert on fire heaters, you should keep on reading API 560. And chances are most of the time you won't go wrong. You will build a very good heater because they have specified all these things. How to weld the anchors, how to clean, what surface should be cleaned. All these type of things are specified in API 560, and they serve you as a very good standard. This is showing the anchoring system of V-shaped anchors you can see over here, and this is a chain link mesh, carbon steel chain link mesh. This is used only for 2-inch installation, 2-inch thick installations in stack or ducts. Yeah, anything more than 2 inches, we use V or Y anchors. These are the guidelines for anchoring for monolithic linings. Generally, 1.5 times the thickness or maximum of 12-inch. For walls, 2 times. For stack and ducts, 3 times. And you can see how the anchors are varied. The orientation is varied to avoid to give more strength to the castable. So this is for the 2-layer design, and that is another reason why people don't like 2-layer designs, is because the anchoring systems become little complex. You have to have a Y anchor. You put this first, weld this Y anchor. The horns are closed. You put the basic layer, the backup layer, then you open this or install this Y portion or the V portion. So it is a little bit more time consuming. But you get a lot better result if you have a 2-layer lining. The only place where we don't put anchors is on the floor, unless we are shipping it. The floor is being shipped, so then we want to put anchors. But other than that, we normally don't put anchors. And there are lots of types of anchors it's showing. So the minimum anchor length is about 2/3 or at least half an inch gap from the hot face is normally what we keep for the anchors. These are all different types of anchors, 3/16 or 1/4 inch anchors you may want to put. For the ceramic fiber blanket, there are different types of anchors which are used, and you normally don't want to go more than 24-inch spacing. You know, uh, these are different guidelines. You can get it in API 560. Again, 10 by 10 inch, 10 by 12 inch, 9 by 10 inch. And these pins are typically 1 inch longer than the thickness of the refractory. That's typically the anchor guidelines. The anchors are depending on the maximum temperature. You can use carbon steel anchors, but normally end users will not allow you to use carbon steel anchors. Most of the time they will say stainless steel anchors no matter what. So those are decided by the tip anchor tip temperature. These are typical linings in fire heaters. Side walls, you use 4-inch blanket or module or 6-inch castable. Floor, you use 3-inch thick 2000 degrees and 6-inch 1600 degrees. Arch 6-inch 8 PCF blanket or module. Convection section 3-inch castable plus 3-inch backup castable. Stack 3-inch or 1.5-inch. Normally 1.5-inch is not used. Normally for good heaters we typically limit it to 2-inch over here. Then ducting. Uh, Another good thing. What comes to your rescue is ASTM. Every castables, every refractory material has been defined by ASTM. So if you specify ASTM or if you specify APFI 60, you will be covered. Firebricks are by ASTM C27, insulating firebrick C155, castable refractory C401. So all these ASTM standards apply. So there is a pretty good safety net which is built in, which won't let you go wrong on the materials. But you have to make sure you specify the correct type of refractory, because here you can see class N, O, P, Q, R. So there are 5 types of castables. So that's where the confusion starts. Service temperature, these are specified by API. For burner, they use 3000 degrees. Target was 28 degrees. Floor about 2500 degrees. Radiant and shield section 1800 is the minimum. Normally you use 2100. Convection section 1800. Breaching and duct 950. So one of the things which is very important is the thermal conductivity of these materials, because that will determine the thickness of refractory what you are going to be using. So this is a comparison of the thermal conductivities of different materials. The unit is BTU inch per hour foot square plus F at 1000 degrees. And you can see the insulating firebrick has a lower thermal conductivity than castable. Low temperature block has even one of the lowest. It's almost as good as the 8 PCF blanket. Then 4 PCF blanket is even this one. This one, I think it's not correct. It should be 15 PCF module. 8 PCF module is not there to my team. But that has, little bit higher thermal conductivity. Another important thing to look about during the lining is the thermal expansion of lining. Because when they become hot, they are going to be expanding. So the designer of the refractory has to ensure that he is providing expansion joints so that when the castable expands or bricks expand, they don't. In ceramic fiber, that issue is not there, but in most of the bricks, most of the castables, you need to provide expansion joints so that you don't get cracking taking place. This is on the brick lining, this is on the expansion in the uh, castable. So refractory failure, what goes wrong? Several things, as I told you, can go wrong. Hot spots, excessive cracking, spalling, erosion, chemical attack, not so much these days. Acid dew point, it happens, especially in the low temperature zones. Partial melting also has happened, not much. Excessive shrinkage has happened. People have experienced failures in ethylene crackers. Anchor failures has also happened. So this is one common cause of refractory deterioration due to length of service. So when the refractory ages, you will automatically start, getting deterioration. And I think after about 10, 12 years, most of the people will have to change the refractory unless it is backup. Common causes of incompatible refractory material. This is a spalled, you can see the material spalled from the roof. This is loss of supports, anchors fell down. Poor installation. I mean, water quality, water temperature, water quantity is very, very important. So, key selection facts, you know, you have to make sure you're selecting the right this thing. So, I have about 10 minutes left. I will try to do justice to the heat loss calculations. So, heat loss calculations are very simple. So, you calculate the heat losses inside the heater using conduction, and then you calculate the heat losses from outside the heater using convection and radiant, and the both should be matching. That is basically, once you are able to balance the QL and QS, you will get the correct heat loss calculation. So it's kind of an iterative calculation. You assume the cold phase temperature, do the inside heat loss, then you do the outside heat loss, and then you see what is the difference between the two, and that will kind of give you issues. So in the lining, it's only the conduction, hot temperature minus cold phase temperature divided by the sum of the resistance or thermal conductivities. So this resistance is thickness divided by the thermal conductivity. So this is the hot flue gas, this is the cold phase, R1, R2, you can see L1, L2. So basically, it's a very simple calculation inside the refractory. On the outside, it becomes a little tricky because there is a convection taking place and then there is a radiant heat loss taking place. So radiation is again by Stephen-Boltzmann equation, HR, and this is the cold phase temperature and this is the ambient temperature. Again in degree ranking. And then we do the natural convection or forced convection. Most of the time we are doing natural convection because that's how API has stated that we do this. So you can find these formulas anywhere. There is again an ASTM. This is, of course, we are giving you over here. HC is 0.53 C into this one, and then similarly forced convection is including the velocity. So even though in real life there is no case where the wind velocity is not taking place, but API for comparison purposes does not recognize wind velocity. He says using wind velocity you can lower the temperature and meet 180. That's not fair. So we always need to calculate using still air. So steps are very simple. Calculate heat transfer area, find the hot phase temperature, assume cold phase temperature, calculate the resistance, calculate the heat transfer loss, calculate the heat loss from the outside, SQS, and then try to make sure that the QL and QS or QW and QS are almost matching and the cold phase temperature is less than 195 for floor and 180. And then you want to calculate the total heat loss, and that will give you. So this is a sample calculation which has been done for a radiant arch, very high temperature, Bridgewater temperature 2120, ambient temperature 80 degrees, wind velocity 0. We assumed a cold phase temperature of 178. So you can see he has already done a lot of iterations and now he is in the final this thing. We have used a 11-inch ceramic fiber module and a backup layer of 1-inch ceramic fiber blanket. Calculate the resistance, calculate the QW, then calculate the heat loss, radiation heat loss, convective heat loss, and did the total. So 213.4 and 214.6 is pretty close. So our cold phase temperature is 178. So pretty simple calculations. So in the end, look at your refractory lining thicknesses. If you need help, you can always call us. We will be able to help you and save you, extend the life of your fire heater, extend the life of your boilers, extend the efficiency, improve the efficiency of your heaters. So thank you. If you have any projects, call us, email us. We have two offices now, and we will be able to help you out. Thank you all. If anybody has any questions, I have about 4 minutes left. If you want to ask me any question, I'll be more than happy to answer these questions. Okay. Yeah, I got a question. Let me see what the question is. Why blankets should be needle type? So this is a manufacturing design, manufacturing. This is how they are done. There are two types. I forgot the other type, which is not different one, but this is a manufacturing. What is the maximum flue gas velocity to be considered for ceramic refractory for stack to stack joint? I think if you have castable, I won't worry about maximum flue gas velocity at all. I mean, most of the time stack velocity is about 85, sorry, 30 feet per second, 30 to 40 feet per second, and castable or brick will be a good material you can use at any time. Okay. Can we use ceramic boards as an insulation backup layer in sulfur gas furnace? Uh, Rakesh, I am not a sulfur plant expert. I have never worked in sulfur plant, so uh, I won't be able to help you out on the sulfur plants. My guess is most of the time you would still be using bricks or castable in those furnaces, from what I know. Yeah, I won't be able to help you out there. Oh, tell us about patents. Okay, so patents, we have three patents. Uh, we have inclined firing technology, which reduces the tube metal temperatures in crude heaters, vacuum heaters, any vertical cylindrical heater, all by almost 100 to 200 degrees F. If you are experiencing high tube metal temperatures, please contact me. We will be able to help you out. There are videos. I've done webinars on inclined firing, several webinars on inclined firing. We have done it on about 12 heaters now. So it's a very simple, and it does not cost much at all actually. You're just inclining the burners and you won't even notice about 3 to 5 degrees. That's how far the inclination is. So you can always call me. Yeah. How to recognize any castable by seeing their chemical composition, whether it is L. So I think that the density will be different. LV1 is to 6 is very light. It has a density of about 20 pounds, 25 pounds per cubic foot. LHV 1 to 4 will be about 53 to 60, 50 to 60 pounds per cubic foot. Uh, I normally don't recommend using LHV. I think most of the companies are getting away from LHV. I mean, unless you have a very high cost pressure, I would assume you would use LHV, but otherwise you won't use LHV. Friends, thank you all. It was a pleasure doing this webinar, and we will keep in touch. I think we will come out with the next webinar very soon. Thanks, and have a nice day. Bye.